Hello guys, welcome to yet another video, and today we're going to look at question 9, which was part of the finals during 2023 November exams for matriculants. So for those who watched my video that I posted earlier in the year, that was a November 2022 paper, you must have smiled when you saw this question because these 5 marks were just being thrown at you. I showed you how to work this out. So essentially those who followed this channel throughout and even just before the exams watched that video, they knew that this was in the bag. All right. So essentially this one is that question in reverse. That question wanted the mass deposited. Now they're starting from the mass deposited to now how much current we should be getting. Anyway, let's find out when we get there. Question 9. Alright, so what do we do here? We are told an electrolytic cell is set up to purify a piece of copper that contains silver and zinc as impurities. A simplified diagram of the cell is shown below. Electrode R is impure copper. Okay, so basically, if this is the impure form, it means this should be the anode, meaning this is the positive end of our electrolytic cell. Now that makes this one where we want the pure copper deposited, and essentially this becomes the cathode, which is the negative terminal of this type of a cell. Now I told you, define the term electrolysis. So obviously these are easy marks, guys. Definitions, we can just say a process whereby a chemical reaction is driven by passing an electric current through the solutions or whatever. All right. This is obviously, there's many ways of, saying this. You can say it is a process whereby electrical energy is converted to chemical energy, or you can say what you call a chemical reaction is driven by a power source or an electric power source. So that is essentially the essence of that definition. Obviously, your teachers teach you to say cram the thing in the exam guidelines and reproduce it as it is. That's okay. That's for safety, obviously. But if you trust your understanding of the subject and the essence of the science, you don't need to cram those things. Otherwise, what's the point of going to school? All right, so write down the reaction taking place at electrode Q. Obviously, the reaction is the pure copper being deposited. All right, so we know that the half reaction taking place there is going to be the copper ions that are from this solution. Obviously, from that anode, they accept 2 electrons. This is usually the copper we work with because nobody suggested otherwise. So we're going to form copper, a solid from the aqueous solution. This is the most likely reaction taking place here. Okay, so let's move on. Now it says, in which direction do the electrons flow in the external circuit? Choose from Q to R or R to Q. Obviously, which one is the positive terminal? This is the positive terminal. Now that means this has been stripped off the electrons, isn't it? So the battery drives those electrons to make these ones a negative terminal because there's like a pool of electrons that came from this. So for the copper ions to accept those electrons to reduce to copper solid. So essentially electrons flow from the anode to the cathode. So that would be R to Q. So 9.3 is going to be R to Q. All right. Easy 2 marks there. So 9.4. Now says calculate the current needed. Oh, by the way, I cannot write on this page. Oops. Okay. All right. Okay. This thing, what is it doing now? Skatlontin. Anyway, so now we want to know. So basically, this is based on this Cu2 plus 2 electrons forming copper solid, that being aqueous solutions. So this is the formula that governs what is going on here. Now, we are given 5 hours. Obviously, that's the time that we need to work out. But now we want to know the current that is needed. And we are told 16 grams of copper were deposited. So what does that mean? This means that the number of moles of copper deposited is going to be the mass of copper over the molar mass of copper. So that gives us a 16 gram divided by, let me just check on my periodic table, because this paper was shared to me, so I don't have that. So it's 63.5. So the molar mass is 63.5 grams per mole. So let's find the number of moles of electrons here of copper. Obviously, I could have done it differently in one step and just do this whole thing, because I'm interested in the number of moles of electrons here. Yeah, maybe let's do that, because this thing of wasting space and time, I don't really like. So what are we interested in, guys? Obviously, when we talk about the current, it means we need charge. So charge, it means the number of electrons, because the relationship is between these electrons and this copper. All right. So essentially, the number of moles of electrons, let's just write it properly. The number of moles of electrons here is going to be, can you see it's 1 is to 2? Sorry, 2 is to 1. So that means if we want the number of moles of electrons, we need to double the number of moles of copper. So it's going to be 2 times the number of moles of copper deposited. All right, great. Now, let's see. This is going to be 2 into number of moles is going to be mass, which essentially is going to be, let's just write it. So this is going to be 2 into, now this was 16 grams. The molar mass is 63.5. All right. So let's do this so that we don't waste too much time. 2 into 16 divided by 63.5. I'm getting a 0, sometimes I think it's best if you leave this like this. Sometimes rounding off is not safe. I'm getting 64 over 127 moles. Sometimes, to stay away from the necessity to round off, you leave it like that. So can you see the number of moles of electrons actually that were transferred or that flowed past a point was this? So now what is the charge of an electron? The charge of an electron is 1.6 times 10 to the minus 19 coulombs. But now we've got number of moles, and we know that the charge per mole, it's the charge on an electron multiplied by Avogadro's constant. That is what we call the Faraday's constant. So essentially, if we've got this number of moles of electrons, so we'll simply multiply this to find the charge. So we can say then the charge of, let's just say the charge here, Q, is going to be equal to, what is the charge here? Charge is basically, or maybe let's just not write Q at the moment. We can say then charge is going to be equal to, basically, Faraday's constant There's plenty ways that you can express this. Multiplied by the number of moles, is it not so? Because that would be the total charge that we have. So now what is Faraday's constant? Is 9,600, 96,500 coulombs per mole. That's what this is. Into the number of moles is 64,127. This is equal to essentially 96,500 into 64 over 127. This gives us a charge of 48629, comma, okay, this is 921 coulombs, right? So that's the amount of charge that we are getting here. And then what do? We can say since Q is equal to the current times the time in seconds, this implies that we've got 48629,921 equals I, which is what we want. The time we're given 5 hours, okay? Now we need a second. Per minute, we've got 60 seconds, right? And then there's 60 minutes per hour, right? So this is 60 times 60 times 5. Great. So this is what we have over there. Okay, say 60 squared by 5. So therefore, our current that is which we want, or that is what we want, it's going to be 48,629,921 divided by this 60 squared times 5. Alright, so that will give us the current needed. So 48629,921 divided by 60 squared times 5. Okay, so this is the current of 2,70 amperes, because coulombs per second is an ampere. So that is the charge needed to drive this deposition of 16 grams of copper onto our cathode. Now, one of you may be asking me, what is that Faraday's constant? Faraday's constant is essentially 1 Faraday is equal to the Avogadro number multiplied by the charge on an electron. So that is going to give us coulombs per mole. Right. This is coulombs per mole. Or is it moles per coulomb? Yeah. Yeah, I think it's coulombs per mole. It's coulombs per mole. Yes. So that is our Faraday's constant. So 1 Faraday is that story. So that means on your formula for constants, you can just simply take the Avogadro number and multiply by the elementary charge on an electron. That gives us the Faraday's. So usually you will get this number commonly used in many textbooks and study guides. But if you don't remember it, you can just use that. You will get more or less the same answer. Okay, so how did you get these 5 marks? Obviously, guys, the number of moles of electrons was important to calculate, and essentially identifying the molar mass of copper in the periodic table is a mark, and essentially finding the Faraday's constant, or whether you remember it from somewhere. But those who watched my video this year, that was in November 2022, Physical Science Paper 2, you will have heard about this and you'll have known about it, so you wouldn't be in trouble. But if you didn't, you just take Avogadro's number or constant, you multiply by the elementary charge on an electron, it gives us this value. rounded off to some decimal places, this is what we get. Okay, so you simply just take that and multiply by the number of moles. As you will see, this is per mole, this is moles. Moles cancel and leave us the coulombs of charge, which is what we want. And then you use your Q equals IT equation. Then you just substitute, but take care to convert those 5 hours to seconds. And that is the answer. So essentially, we've got our marks there. And then this is a mark because finding that charge is important. And essentially, this conversion of time is important. The answer is important. So this is how those 5 marks could be scored. Of course, there's plenty of other ways you can look at it, but it's not a big deal. All right, so let's move on to the last question. So 9.5 says, during this electrolysis, only copper and zinc are oxidized. Okay, and then the question says, give a reason why silver is not oxidized. It's only because silver is a very weak oxidizing agent than these two. So we can just say silver is it's a weaker reducing agent actually. It's a weaker reducing agent than zinc and copper. As we know, it is more of a stronger oxidizing agent rather. So that is the reason. So this is again your last 2 marks. So this is how you could take these 12 marks with a smile on your face, especially knowing you have seen this thing before, but rather put differently. So that is the most important thing. So this is a bit of stoichiometry applied in chemistry and bringing out also electricity. So guys, be careful of these kinds of questions. They always like them for the finals as well as for the supplementary examinations. So master these and be the best. Okay guys, I'll see you next time. Bye bye.